Hi there, students. This is Dr. John, your physics and math professor. Today we're going to be working on another circular motion problem. This comes from the 50 or 100 years ago at the old country fair. There'd be a stunt set up, something like this, with a lot of people watching. We'd have a big long ramp where people would take their bicycles down and then see if they could stay on the loop all the way around. Of course, this was very dangerous. Don't try this at home. But what we can do at home is we can do the physics calculations for this. So here's the problem. A bike goes around a loop with a diameter of 10.0 meters. How fast must it go? And this problem is a little bit different than, say, a Ferris wheel or something like that. So if this was a Ferris wheel, if we had a chair here and if we had a chair here and on the side, the velocity here, at least the absolute value of the velocity here, would be the same as the absolute value of the velocity here. The vector direction would be different, but the absolute value of the velocity would be the same everywhere, because everything in a Ferris wheel is locked together. Everything is rigidly locked together with metal, so it all has to go at the same velocity. However, in this case, obviously the bicycle will be accelerating down here and will reach a maximum velocity down here, and then it's going to probably slow down a little bit because some of the kinetic energy from the bottom will be converted to potential energy at the top. Mind you, the bicyclist can continue to pedal as well. So what we're looking at here is not the more complicated question of what would be a bicyclist speed at the bottom if then they stopped pedaling and we wanted them to stay on, but just simply what velocity does this bicyclist need to have at the top to stay on the ramp and not fall down. Now here we have a couple of different forces drawn with regard to this ramp. Here we have the bicycle at the top. What forces will this bicyclist feel or cause? Well, for one, obviously, this purple one here, the bicycle will have a mg, a force of gravity going downward. So that's going to be, force of gravity is going to be like this. Force of gravity is equal to mg. The mass of the bicycle and the rider, as well as the acceleration of gravity. And then it's also going to experience this fake gravity. It's actually, according to Einstein, it's a real gravity because it's a gravity caused by acceleration in this direction. We call that the centrifugal, like a centrifuge spins things to try to separate things according to mass and density. So this would be centrifugal acceleration outward. It's a force that this person would experience outward, caused by the fact that they're actually accelerating inward. Please don't get this confused as I share a couple of these things here. So this bicyclist is going around, they're going this way, and then they have to accelerate a little bit this way. Then they're going this way, they'll have to keep accelerating this way. So they're going to have to keep accelerating toward the center. What is it that causes this acceleration toward the center? This thing that we call the centripetal or centripetal acceleration, which is ironic because we're on a bicycle, we're pedaling. This acceleration toward the center, this centripetal acceleration, has to always be toward the center. It's going to be caused by the normal force, the inward pressure of this wooden ramp that's built for them. It's constantly going to be pushing in this direction, causing the bicycle to accelerate in this direction. And just like the illustration of the elevator, when the elevator is accelerating upward, you who are standing in the elevator feel like you're heavier. You feel a force downward. That's like an artificial gravity caused by the upward acceleration of the elevator. In the same way here, this bicycle is accelerating inward. It's caused by the wood of this ramp here. It's accelerating inward. That's going to cause this centrifugal force outward. It's going to cause this apparent gravity outward. So what's really important here is that the gravitational force, the gravitational pull on the rider that wants to pull the rider off here, has to at least be equal to the centrifugal force outward. Because if it's not, then this thing will pull him downward and the rider's going to fall off. So we have to at least have this thing. Now, what is the value of this centrifugal force? It is exactly the same as the acceleration inward. And remember, the centripetal force inward is equal to mv squared over r, where r is the radius. I've written that in here, radius of 5. We're given the diameter here all the way across, so the radius would be half of that. The radius would be 5. The velocity is just simply the velocity at any instantaneous point. We're concerned about the velocity at the top. We want to know how fast must it go at the top. So that's the velocity we're concerned about here. And if we now take this biker and we say the biker's going to experience a force of gravity downward that wants to pull him off the ramp and make him fall, that has to be exactly equal to the centripetal acceleration that he's experiencing inward, caused by the ramp, this centripetal acceleration inward is also going to be equal to the outward force that he feels, which we call the centrifugal force. These two, the centripetal and the centrifugal, are equal in this case because the centripetal acceleration is the acceleration that this ramp pulls him inward with a normal force, which is equal to, just like in the elevator, the extra force outward. So in that case, if these two are exactly equal, he'll just stay on there. Actually, the wheels of the bike may just leave for just a second. He'll feel weightless, and then his weight will start to increase again. So this here, we want this to be equal to this. Now, if we have those two equal to each other, I'll just write this over here. So this is going to be equal to mv squared over r. I've just rewritten this up here. So I don't need this anymore. I don't need this anymore. We want those two to be equal. The mass of the bicycle and the rider don't matter. They cancel out. And we can take this r to this side. So I'm going to cancel that out, get rid of the m, and move the r to this side like this. So v squared is equal to r times g. Let me rewrite that. So if v squared is equal to r times g, then v is equal to the square root of this. So we'll just simply do that. And what are those actual numbers? Well, we've got the numbers here. We have 5 being the radius, and the acceleration of gravity is 9.8. Big square root around that. 5 times 9.8 happens to be 49. So v is equal to the square root of 49, which is equal to 7. The exact value for that. So we'll have the velocity at the top that he needs to have to stay on there is 7 meters per second. Now notice here, just to finish this problem off, we have 3 significant figures here. Even though this looks like an exact answer, we'll still put 3 significant figures in there. So 7.00 meters per second at the top. Now, for a normal, a very strong Olympic athlete, they can probably run at 10 meters per second. So that's a fairly good speed the bike needs to have at the top. And remember, it's going to lose some speed from here to here because you'll have to convert some of this kinetic energy to potential energy. So unless the person continues to pedal, you're going to have a higher speed than that here. So it's a fairly good speed. You're going to hit this. You can't go full speed because you still have to stay on the ramp. You still have to control your steering and everything. You don't want to lose control of your steering. Like I said, it's dangerous, but doing this calculation is very safe. And I hope you enjoyed it. If you did, like and subscribe. I will see you in the next video. Bye-bye.